We are now on to the acid-bases unit. What we're going to look at today is general properties, a couple definitions, the Arrhenius, the Bronsted-Lowry, and the amphoterism definitions, along with some nomenclature again. Alright, so here's some typical properties of acids and bases. First off is taste. Acids tend to be a little bit sour. Think of it like citric acids in grapefruit, lemons, acetic acid, and vinegar. And then you have like bases, which is soap. Please don't try this at home. Don't be licking soap. Just know that it tends to have this like bitter taste. When they get on your skin, acids tend to sting. They hurt. Whereas bases are slippery. Think of, again, soap. When you wash your hands, your hands typically get slippery. All right. One thing to note with acids, they typically react with active metals to produce hydrogen gas. Now, if you think back to the activity series when we were looking at single replacement and we did the silver penny, which we coated in zinc. When we put the zinc into we had a zinc solution, we put the pennies, we took the pennies, which when you scratched on the, scratched the sides, open it up to the zinc, when you put them into the hydrochloric acid under the hood, I had you look at them, I'm like, what do you see? You all mentioned, it's bubbling, it's moving, it's bubbling. The bubbles was when the zinc was replacing the hydrogen in the hydrochloric acid. Another thing to note, they are both, acids and bases are electrolytic. We'll get into that in a little bit, but they are electrolytic. They also change color of indicators. Now, if you have any type of pool or a spa or something like that, you might be checking the pH balance. Those are indicators. You're checking the indicators. If certain flowers change colors depending on the pH of the soil. Last but not least, acids neutralize bases. Bases neutralize acids. All right, so the first real definition that we're going to really look at is the Arrhenius. So in 1830, scientists recognized that all acids contain hydrogen, but not all hydrogen-bearing compounds are acids. For instance, when you have C6H12O6, that is sugar. Sugar is not an acid. It just happens to have hydrogen in it. Savante Arrhenius linked acid behaviors with the presence of a hydroxide ion and the behavior of bases with the presence of hydroxide ions. So Arrhenius, again with acids, they produce hydrogen ions as the only positive ion in solution. So we have HCl goes to H plus Cl plus. This should look kind of familiar if you think back to the net ionic equations. We are going to be seeing this a little bit more as we go on. This can also be written as hydrochloric acid in water gives you a hydronium ion and chlorine ion. So the hydronium ion, the H3O plus is hydronium, a water with a hydrogen ion attached to it, or to one of the oxygen's unshared pairs of electrons. Remember, oxygen has two. I believe it has two. But it does share, and we'll see it in just a second. It is listed on the polyatomic ion table in our reference table. So looking at this is, again, a formation of an acid. You have your acid, so it's a hydrogen connected to something. In water, two unshared pairs. The hydrogen pops off this, leaving its electron there, and floating over and attaching to the the water to make the hydronium. And then you have the negative ion over here. So the small hydrogen ions interact strongly with non-bonding pairs of electrons on water molecule to form the hydrated hydrogen ion, hydronium. The hydrogen leaves its electron behind when it makes its move, and this produces the ion in solution, the negative ion in solution. Oh, pardon me. This makes an acid and unique molecular compound because it's electrolytic. It can conduct electricity. So chemists use the hydrogen ion and the hydronium ion interchangeably. They kind of just switch them, as you can see. Whatever one they want to write, that's the one they can write. All right? So a base, Arrhenius base. This produces hydronium ions, or hydroxide ions, which are negative in solution. So sodium hydroxide. We've seen this. We use that. That was in the zinc. When I did the zinc with sodium hydroxide, it was what you put the pennies into. That's what we use for this. So metal hydroxides are typically bases. Bases are electrolytic because they are generally ionic. Ionic can split in solution. But you got to be careful. Not all bases have hydronium. Ammonium, our little special case, is a very important base, but it does not contain the hydroxide ion. Again, you can see this ion in the polyatomic ions in your reference table. So NH3, ammonia, and water gives you ammonium and hydroxide. All right, so we're going to classify the following as a base, acid, or neither. So let's look at this. This is a hydrogen and a bromine. If I split them up and give my net ionic equation, I've got a hydrogen plus ion and a bromine minus ion. It produces the hydrogen ion, which causes it to be a base, an acid. So potassium hydroxide, it has hydroxide right in it. So you know if there's a hydroxide, has to be a base. NaCl, it's sodium and chlorine. No hydrogen, no hydroxide. It is neither. Zinc hydroxide, again, it's got hydroxide right in there. So you know it's a base. Rubidium chlorine, it's neither. And then hydrogen chlorate, I want to say, is an acid because you've got that hydrogen. So nomenclature, how we call these things. Bases are super easy. You heard me just calling them by their names. It is something hydroxide, named like any ionic compound containing a hydroxide ion. Acids, however, special. They require a little bit more effort. So acids can be either binary or tertiary. Binary means there are 2 elements in it. Tertiary means 3 elements. Binary acids, that H plus a second element. Hydrochloric acid. Now, why did I say ic? Because you do hydro and then the anion ic. So hydrochloric instead of ide. Hydrochloric acid. And this is hydrogen and sulfur. So hydrosulfuric acid. And you want to say sulfuric, because sulfuride, you're just, instead of ide, you're doing ic. And the first acid contains only 1 hydrogen, chlorine, you see this. And the second one, 2. But they are still hydro. We're not giving it the dihydrosulfuric. It's hydro. Okay, so tertiary, that's 3. 1, 2, 3. So the thing we got to remember is if it has ite, polyatomic ion, ite, you're going to name the acid us or end with us. Whereas for ate, you end with ick. So this is going to be nitrous, a nitrite ion, sulfate ion. So it's going to be nitrous acid and sulfuric acid. Notice I don't say hydro, only hydro with binary, with 2. If there's no 2 and there's 3, it's just the second part, acid. So the NO2, the nitrous, nitrite ion requires only 1 hydrogen, while the sulfurate ion requires 2. Okay, so are they binary, tertiary? What's the correct name? So let's see how many elements there are and then name it. So 1, 2, 3. I believe this is perchloric acid or chlorous acid. It's tertiary. 1, 2, 3. There's 2, so it's hydrobromic acid. This is 3. Nitric acid, tertiary. 3 again. This is phosphoric acid. This is sulfuric or sulfurous. Sorry, that's my bad. Sulfurous acid. There's 2, so it's binary. Hydrofluoric acid. Yes, hydrofluoric acid. All right. The lovely thing is they're named for us. We just have to look at table K. We look right underneath it to table L. Gives you common bases. So you've got sodium hydroxide, potassium hydroxide, calcium hydroxide, aqueous ammonia. So there's that AQ. All right, so let's look at some Bronsted-Lowry. So Arrhenius, useful but restricts acid bases to aqueous conditions only, whereas Johannes Bronsted and Thomas Lowry proposed a more general definition which involves the transfer of hydrogen ions from one molecule to another, where a hydrogen ion is simply a proton, its single valence electron has been removed. So acid is any substance that transfers a hydrogen to another molecule. This would be a proton donor. It gives it away. So it's an acid. A base is anything that accepts that hydrogen, a proton acceptor. So let's look at this. This goes from hydrochloric to chlorine. It is donating. It's giving it away. So that is the acid. This over here is accepting the hydrogen. So it is the base. Reading right to left, hydrogen transfers the hydrochloric acid to the water base. An acid and base work together. They neutralize each other. An acid donates, the base accepts. We cannot have one without the other. Reading from right to left, the hydrogen transfers I'm going back this way, the hydronium ion donates while this accepts. So this is the acid, that would then be the base. Because every reaction will eventually proceed in the opposite, the reverse. Each acid-base reaction will have 2 acids and 2 bases. Now they have special names to it. Remembering it has to have a hydrogen to be able to consider an acid, because chlorine is by itself. There's no hydrogen. It has to be a base. So what are these called? They're called conjugates, the opposites. The conjugate acid-base pairs, 2 substances that differ only by the presence of the hydrogen ion. The molecule with the extra hydrogen is the acid. So this has the extra, so there is the acid with its conjugate base. Here's the base with the conjugate acid. Since the acid donates or loses, the charge decreases by 1, whereas the base adds 1, so it increases by 1. All right, so many Bronsted bases contain the element nitrogen, which has an unshared pair of electrons to accept the base. Okay, I'm going to end here. If you have any questions, please let me know, and I hope you guys have a great day.